Hello, welcome back to Engineering Dynamics. We have finally entered in to finals week, and I think I'm going to jump on here and walk you through one super long, freaking annoying problem. I know, but once we get through it, you're going to be like, what? This is awesome! In this problem, we are going to use rigid bodies. We are going to see pure rotation, planar rotation. We are going to use two different equations of motion. And we're also going to use kinematics. We are going to need to use relative motion. And I think that's it. Oh, and I'm going to teach you how to solve a systems of equations using matrix form, so you can use your calculator, okay? Okay, if that interests you, stay tuned. Oh, and by the way, don't forget to like the video and subscribe. It says the system is in equilibrium in the position shown. If the mass of the slender bar ABC is 6 kilograms, the mass of the slender bar BD is 3 kilograms, and the mass of the slider at C is 1 kilogram, the spring constant is 200 Newton meter, and it's asking if a constant 100 Newton downward force is applied at A, what is the angular velocity of bar ABC when it has rotated 20 degrees from its initial position? Are you ready? I'm ready. Okay, first thing I want you to do is ask yourself, are we living in rigid bodies or in particles? This can't be modeled as a particle. We are definitely in rigid bodies. How many rigid bodies are there? If you said 2, no, there are 3. The slider does count for a rigid body, okay? So there are 3 rigid bodies, which means we are going to have 3 free body diagrams, okay? Also, next question, are there forces involved? So are we living in kinematics or in kinetics? There are forces involved in this one. We clearly have a spring present, we have some weight going on, and we have a constant 100 Newton downward force. So there's definitely forces. So we definitely have some kinetics. To solve problems that involve kinetics, we need to use equations of motion. What are the 3 equations of motion? There are 3 equations of motion. You're going to have a Newton-Euler, work and energy, impulse and momentum. For the system that we have now, which equation of motions do you think that we're going to use? Okay, if you have a hard time answering this, you need to write down, okay, I know I have a spring force, and a spring force is a function of position, right? So that means that we are going to use work and energy. So we have work and energy, and that is going to be used when we have forces as a function of position. I also have just regular forces that are present. I'm going to have my reaction forces that are unknown. I'm going to have that 100 Newton force that's there. I'm also going to have a reaction force at the slider. So I also am going to need to look at the Newton-Euler. And that is when forces or moments are just, they're not functions. They're not functions of anything. The third equation of motion is impulse and momentum. So if you have a force that is dependent on time, then you would use impulse and momentum. Going back to work and energy, it's a function of position. How many positions do we have? Well, we have our first position that we start out with, and it's a function of time, right? So if it says that this is in equilibrium, meaning that it's not moving at all, so its first position will be at 50 degrees. So I can say that P1 is theta equals 50. At P2, it states that I want to know the angular velocity of bar ABC when it's rotated from its initial position. So I'm going to push down on this bar with 100 Newton force, and that bar is going to push the spring that means that this angle is going to decrease by 20 degrees, meaning that my P2, my theta equals 30. Okay? All right. Also, no, I think that's good. Okay, so now we need to, what we've done so far is kind of list, where am I in the problem? Your next step that you need to do is say, okay, what are my steps to solve this problem? Our first step is you need to draw your free body diagrams, and they need to be complete. So we're going to go through that in this video. Your second one is you need to use your kinetics, okay? And then your third, you need to use your kinematics. As we go through this, we want to make sure that we have this roadmap with us at all times, because you are going to see that you're going to do a lot of work to find one parameter. You're not going to remember why you were finding it in the beginning, okay? I don't want you to get lost along the way. So, all right, let's go ahead and start with our first step, which is our free body diagram. We have 3 rigid bodies, so technically you're going to probably need 3 rigid bodies. For this one, you could get away with 2, so we'll see. But we have bar BD. Bar BD is some theta from the horizontal, depending on what position you're representing. At point D, it's an external pin, so you're going to have reaction forces in the Y. You'll have dy, and you will have dx. When it comes to a reaction force, it means that it's limiting you in that direction. It's taking away a degree of freedom. So if it can't move vertically, there has to be a force that says you can't move this way. And if it can't move, so if it can't move vertically, you have to say that there's a force that says you can't do it. If it's horizontal, you can't go that way either. So these forces are opposing that motion. Okay, I don't have a reaction moment because this is a pin. That bar is allowed to rotate. Okay, I also have a weight present. The weight is going to act at the center of mass. So this is the weight of BD. Okay, and then I also have my reaction forces at B. So I'm going to have Bx, and I'm going to have By. Anything else on this free body diagram? I don't think so. So let's go ahead and draw the ABC bar. So that goes here. As always, we have a weight acting down. So we have our weight as A, B, C. At point B, we will also need to transfer these forces. So you need to transfer these forces over. To transfer them, you're going to do equal but opposite. So on this one, I'm going to make Bx positive, and I'm going to make By positive. I also need to represent the downward force at A, so I'm going to call it the force at A. I also need to represent my spring force. So this is my spring force. And then what type of reaction forces is a slider going to give? It's going to produce a normal force. And again, it's just because that force, it's saying you can't go up and down, okay? I'm not going to have a horizontal force because I'm allowing you to slide, okay? All right, and it's a pin so you can rotate. So you only have one reaction force. Now, I want you to take a look at the geometry. Oh, so you also have a theta, so let me draw this in and then we'll look at the geometry. We have some measurements here. We have the length here is 1. This is also 1. And this is also 1. So we have an isosceles triangle. That means that at the rate at which this rotates, let's do blue. So this one's going to rotate this way if I'm pushed down. So that's going to be a positive. So it's counterclockwise. So it's a positive omega ABC. It's an isosceles triangle. So that means that this one, which is moving in the opposite direction, omega BD, These are going, we can say that omega ABC is equal to negative omega BD. So our scalar, like just the value of omega, is going to be the same, but their directions are going to be different, okay? So now, so my free body diagrams, that's really pretty much it. You can do a free body diagram of C if you want. I just want, I don't think it's going to be necessary in this. We can come back to it if it is. Before I move on, I do want to establish what type of rigid body motion each part is undergoing. So for bar BD, it is undergoing pure rotation. So we have pure rotation here. Bar ABC is undergoing planar. And the slider is going to be translational. Okay, I think now we have a really good free body diagram, and we can move on to kinetics, okay? Before, like in kinetics, we know that we're going to use Newton-Euler and work and energy. And in those equations, we use I, okay? So you can either calculate I now or later. I would say let's do it as we go, okay? So we're done with the first one. Let's move to the second. So our second is kinetics, and we said the first thing we're going to do is Newton-Euler. It doesn't matter if you decide to do work and energy first. The problem is you're going to see that there's a lot of unknowns in that equation. You're going to have to go back and do this anyway. So you can either start by writing out work and energy and seeing how many unknowns you have and then developing more equations for that, or you can just start out with this. I usually like to start out with Newton-Euler anyway, but it's up to you. My voice is very hoarse in this video. My little boys play soccer, and I think I got a little bit too excited. I was a very proud mama, and I'm losing my voice. I am so sorry. I hope this doesn't sound too bad. Anyway, so we have Newton-Euler. So we're going to start with bar BD. Now, you have two positions. Newton-Euler does not deal with position. Your forces in your moment have to be constants, okay? They cannot be a function of anything. It has to be a constant. So before you start, you have to decide, am I using Newton-Euler in position 1 or am I applying it to position 2? For this problem, I would suggest you do everything regarding position 1. And that is because in the problem it tells us in the position 1 it's equilibrium. That means that A and alpha are 0 at position 1. And there's something else too. So we have A, which equals alpha, which also equals FA equals 0. Because at position, the first position, you haven't applied that downward 100 forces, 100 newtons yet. So it equals 0. So if you decide to use all of the Newton-Euler equations at position 1, all of your equations become much simpler. I would suggest analyzing it at this position. So let's do that. Let's do the sum of the forces equals MA. Now, when you're taking an exam, you need to ask yourself here, what type of coordinate system am I in? In my free body diagram, I did X and Y, so I can break this up into X and Y's, okay? So I'll do the X first. Again, A is 0 because of equilibrium. My forces in the X is going to be dx minus bx equals 0. This is my first equation. I'm going to do the same thing for the y. Again, my acceleration in the y is 0 because it's in equilibrium at position 1. My y is going to be dy minus my weight of bd minus by equals 0. My weight, why don't we go ahead and calculate the weight of bd is going to equal mass times gravity, which is 29.43. And that's just because they had given us a mass of 3. So I did 3 times 9.81. And then for the weight of ABC, you need to do 6 kilograms times 9.81, which is going to be 58.86. So here I'm going to say that this is dy minus 29.43 minus by equals 0. This is equation 2. Okay, now I want to, that's all the newtons that I can use for that bar. So I think I want to create a moment equation. So if I do the sum of the moments are going to equal I alpha, this is Euler. Again, position 1 is in equilibrium, so there is no motion. And now I can do the sum of the moments. For this one, let's go, which point should we take it about? Because you can take the moment about any point you want, but we do want to be a little strategic about this. If I take it about point B, then I get relations of things that I really can't use, right? If I take it about the center of mass, then I have another 4 unknowns. If I decide to take it about dx, dy, bx and by are shared points between the two free body diagrams. So I think I'm going to do it that way. Is it a must? No. You can do it at any point you want, and then you just keep developing equations that you know, until you get what you have, right? Until you get enough. All right, so let's look at our moments. We know that if we go about D, we're going to have a weight, our weight, and our weight is going to create a clockwise moment, so that's going to be negative 29.43. Our weight is going down, so we need the perpendicular distance. Our weight acts at the center of mass, which is 0.5 length, okay, because the bar is 1, so it's 0.5. So this is going to be 0.5 cosine 50 plus bx is going to contribute. So we have bx, that distance would be sine 50. And we also have by, a distance cosine 50. If I calculate all of this out, I am left with 0.766 bx minus 0.46 by minus 9.5 equals 0. Okay, this is equation 3. And all I did was, you know, use a calculator and calculate that out. Okay, so now what I want to do is go to bar ABC and do the same thing. So I'm going to do the sum of the moments, or I'm sorry, sum of the forces equals MA. Again, we are still analyzing position 1, so that's going to be 0. I'm going to do the sum of the forces in the x direction first. So I'm going to have BX minus FS equals 0. I only have 2 forces in the x. Okay, so what about the sum of the forces in the y? Oh, so this is equation 4. So the sum of the forces in the y equals MA. A is 0. It's in equilibrium at position 1. So for my y, that one I'm going to have Fn, my normal force. I just called it n in the free body diagram, but same thing. Plus By minus Fa minus 58.86 equals 0, because that's the weight. So I have, okay, so that's equation 5. We are rocking and rolling. How many unknowns do we have right now? I believe there's 6, but let's count them up. We have, let's write them out at the same time. And you could have done this at the beginning to guide you. So we have Bx, By, we have Dx, Dy, we have the normal force, and we also have the spring force. 1, 2, 3, 4, 5. We have 6. So I need one more equation. I'm going to go ahead and put in the sum of the moments. equals I alpha, position 1, it's in equilibrium, that goes to 0. Now, again, we have to pick a point. I need you to understand that we are using Newton-Euler, which means that the forces that we're looking at, they have to be constant. They can't be a function of anything. So I immediately look and say, I really want to take these moments about C, because that will get rid of my FS, okay? Yeah, because FS is a function of position, okay? So it doesn't matter, again, probably not. You just need 6 equations, 6 unknowns. I just am going to choose to do it that way. All right, so this moment, if we take it again about C, we will have FA will create a positive moment. Its perpendicular distance is 2 cosine 50, because again, position 1. Then BX is going to be a negative moment at sine 50 minus, because BY will have a negative moment. Its perpendicular distance is cosine 50, plus now we have the weight, which is going to be 58.86 cosine 50 equals 0. If I work that all out, I am going to have 1.29 FA minus 0.766 BX minus 0.64 BY plus 37.8. And that is going to be, yep, equals 0. Okay. So now I am going to want to clarify one thing. I did leave FA in, but in this position, what is FA? In position 1, FA is 0, so that takes it out of here as well. But that wasn't an unknown that we listed, it's a known. But anyway, so this is equation 6. So 6 unknowns, 6 equations. Oh boy, how do I handle that? Well, if your professor allows you to have a calculator, I let my students, sometimes I do ask them to clear the memory of it, but I don't see a problem with it. There are 2 ways you can do it on a calculator depending on which kind you have. You can use a matrix, which I prefer to do. When you go up to higher level courses, I know robotic arms definitely uses it. Almost all uses matrix, right? Or you can use system of equations. If you use a matrix, this is how I set it up. I don't know how to use the system of equations in a calculator, so I can't teach you that. But I can teach you this. The first thing that I like to do is list all the parameters that I'm using. So I'm using FA, BX, BY, DX, DY, FN, FS, and I have some kind of constant in there because of that weight. So I have a constant, okay? These are going to help keep me organized, okay? They're going to be the coefficients of what I put in the row. The columns are going to be my equation 1 all the way down. I have 6 equations, so I'll have like equation 6 down here. And then I'm going to multiply it by this row. This row does not go in your calculator, but it is a good sanity check. So I usually just pop these in here. Stick with me. It will make sense when I run you through it. Okay, so if you look at equation 1, so equation 1 is up here, this guy right here. So if we look at equation 1, do I have an FA in there? No, so I'm going to put a 0. Do you have a BX? Yes, I have a negative 1 BX, so I'm going to put negative 1. I have no BY, that's 0. I have a negative DX. I don't have a DY. I do not have an FN. I do not have an FS. And my constant is 0. It's set equal to 0. Same for equation 2. Does equation 2 have Fn is 0, Bx 0, By 0, dx0. Oh no, we do have a by. Did you see that? It snuck in. Take a look here. So we do have a by. So we have a negative 1 by. Then we have dy as negative 1. No fn, no fs, but we do have a constant. Now, I want you to set the equation, so the way you put it into the matrix is that this you don't want it to equal 0. I'm going to have it equal whatever my constant is. So the correct form to write this in is going to be negative dy minus by equal 29.43. Okay, so on here I'm going to put 29.43. Okay, equation 3, I'm going to have, I don't have any FAs. BX, I have negative 0.766. BY, I have negative 0.64. DX is none. DY is none. FN is none. FS is none. Now my constant, remember that I have to take this term and move it over. So it becomes a positive 9.5. Now I have equation 4. Equation 4 is negative BX minus FS. So I have 0, I said BX, yep, negative 1, BX, 0, I have DX is 0, yep, I just have an FS, so 0, 0, 0, negative 1, and my constant here is 0. Okay, equation 5, we have FN by, so our FA is 0 because it's position 1. We have no BX. We have no BX. We have 1 BY. We have 0 BX. And we just have a constant, right? Is there any more? Oh, no, I have an FN. So I have a 0, 1, 0, and then my constant is going to be a positive because I'm going to bring that 58 to the other side. So it'll be positive 58.86. Okay, my last one, I have 0, negative 0.766, negative 0.640. Just locate your matrix function. You're going to open that function and you're going to see 3 headings. We have names, math, and edit. A lot of you, if you've never used this before, you're going to see all of these. Basically, it's going to be empty. There's nothing going to be there. It's just because you haven't defined anything yet. It's not a big deal. We're going to go scroll over to edit, and I'm going to just edit A. You can edit any of these. Just edit any of these that you want. I'm just going to edit a random one. Let's pick C. And you have to enter in how many rows and how many columns. We have 6 rows because we have 6 equations, and we have 8 columns because we have those 8 parameters. So in our first cell, we need to put a 0 because that's what we had in our previous, right, in our matrix. We're just basically putting our matrix into here. So our next one is negative 1, 0, 1, 0, 0, 0, 0. Our next row is going to be 0, 0, negative 1, 0, 1, 0, 0, 29.43. Then we have 0.766, negative 0.64, 0, 0, 0, 0, and in the last column we have a 9.5. Okay, then we have in our fourth, we have 0, 1, 0, 0, 0, 0, negative 1, and 0. Okay, our fifth, we have 0, 0, 1, 0, 0, 1, 0, 58.86. Then we have 0, negative 0.766, negative 0.64, 0, 0, 0, 0, negative 37.8. Now what I want you to do is quit. I want you to then go back to matrix, but this time I want you to scroll over to the math tab. Okay, then you're going to scroll down and find R, E, F function, push enter. Go back to your matrix and select the matrix you put that data in, push enter, and then push solve. Now, the first column you see is all zeros. So that is going to tell you that your first parameter, which was FA, does not have a solution, and that's fine, we didn't need one for that. Your second row does have a 1 here. That means that it does have a solution, that's BX. This is BY, DX, DY, FN, FS, and then if you scroll all the way over, those are your answers. So your first one, your BX is 30, BY 22, DX 30, DY 51, FN 36, FS 30.87. So your calculator should produce BX equals 30.87, BY equals 22.11, DX equals 30.87, DY is equal, DY is equal to 51.54, FN is equal to 36.57, FS is equal to 30.86. Pause here. This number, what is this, what FS is this really? The force of a spring is a function of position. It is not a constant. We analyzed it at position 1, so really this is FS at position 1. So you did all of that just to find one force because you don't actually need anything else but the FS1. I know, this is where you go back up and you say, you know what the heck? I just did all this work. And you are going to say, it's okay, I'm going to follow the map because Dr. Walk said it will work. So here you're going to say, I did Newton Euler. Now I'm going to go to work and energy and I'm just going to keep on going and say a prayer. Okay, so let's now move to work and energy. Because our whole job is to find omega, right? And work and energy is going to be the integral of a force in terms of its displacement is going to equal 1/2 linear kinetic energy plus 1/2 angular kinetic energy. Okay, and there is, that omega is what I'm looking for, okay? But I need this side, which is going to be your potential energy, okay? So potential energy, we have to list all the forces that do work in this problem. Can you name the forces that do work in this problem? Just by looking at this. Well, we know FS is going to do work because that is its changes with displacement. We know FA is going to do work. We know that weight of the bars are going to do work as well. So I think that's all the weight we have. I think that's all the ones that we have. Yeah, so we're going to go down here and we're going to list all the forces that do have potential energy in them. I use V for potential energy. So we have FA that does work. We have our weights that do work. BD. I don't even know what that is. Okay. And we also have the spring. So let's just focus on the potential side, okay? So we can say the FA, D, now FA is starting from one height position and ending at another height position. So it's just displacement is a change in height. And it is going to go from the position 1 to position 2. Now, the force FA is going this direction, and my height change is going in that same direction, which means that my answer is positive. If the force was going in the opposite direction, then the displacement, it's going to be a negative answer. So again, if force is in the same direction as displacement, positive, okay? So this is going to equal 100 newtons. Now, my integral would be h, and I'm going to evaluate that from h1 to h2. The height of the first one, if we scroll up here, we have, so if we look at the height of the force here, what is the vertical height? Well, the vertical height would be 2 times cosine theta, right? It's that vertical distance. So this would be 2 sine theta in position 1 is 50. This would be 2 sine theta in position 2 is 30. If I make this calculation, I should get 53 Newton meter. I want to save that. Okay, so this is our first one. Now I need to calculate the potential energy of the weight for bar ABC. So again, we have H1 to H2 and the weight of the bar ABC. We calculated that weight and it was 58.86. Again, it's a change in height. This is going to equal, again, the weight force is going down and my displacement's going down, so it's going to be a positive number. Here, we are going to have 58.86 H. It's going to be evaluated from H1 to H2. The weight of ABC, right, the location of that's going to be halfway. So now the vertical distance would be 1 sine. So for here it would be 1 sine 50, and this would be 1 sine 30, and this is going to equal 15.57 Newton meter. Let's do the same thing for the weight for bar BC, or I'm sorry, BD. So we have height 1, height 2. The weight of bar BD is 29.43, and that's DH. This is going to equal, now my height for this one, again, it's at the center of mass here, so it's going to be half the distance, so that's 0.5 sine theta. 0.5 sine theta. So my height 1 would be 0.5 sine 50. 2 is 0.5 cosine 50. All right, so this would give you 3.91 Newton meter. Okay, so we are done with this one, and now we have left our potential energy due to a spring. So again, we have our equation. This time our displacement is a distance that we usually use S, so I'll put S here, not a height, but it's just displacement. Okay, so this is going to equal KS ds from S1 to S2. Now, my displacement is going to be different than the direction of my force. They're in opposites. So the direction of my spring force is going in this direction, but my displacement, it's becoming shorter. So that means that this has to be a negative, okay? So this is going to equal 1/2 K S2 squared minus S1 squared, okay? We found earlier, FS1 as 30.86. So let's bring that down here. FS1 equals 30 point, what did I just say? 86. And I set up here that Fs is equal to Ks, right? So if I divide by K, I should be able to find S1. So S1 equals my force, 30.86, divided by my spring, and my spring constant, I believe they gave me, was 200. So I'm going to divide this by 200, and I'm going to get 0.154. To get, because we still need S2, S2 is going to be whatever the spring was for S1, whatever that movement was, plus the distance traveled by the bar, right? So that's going to be S1 plus, we're going to do 2 cosine 30 minus 2 cosine 50. So this is the distance traveled between the two positions plus the initial travel. Okay, so you should get an S2 equaling 0.601, which is good. That makes sense. It's more than S1. So I'm going to plug these in here, and I should get a potential energy of negative 33.74 Newton meter. Now, all of these that we just collected are going to only be your potential energy. So your potential energy, your V, is going to equal 53 plus, the first one we found was 53, right? Yep, 53 plus 15.57 plus our 3 and plus minus our 33. Okay, so we're just gonna, this is just bookkeeping here. So we have 15.57 plus 3.91 minus 33.74 is going to be the V. All right, but in our equation, remember that we had F dx equals the change in kinetic energy. We only looked at this part. Now we need to look at this part, okay? So why don't we, and this is the change in kinetic energy. Usually we use the letter T. So I can say that T2 minus T1 that's what this equals. So this right now is going to be V equals, so V is all of these that we just added up, equals T2 minus T1. What is the kinetic energy at position 1? Well, kinetic energy is all related to velocity, whether it's linear velocity or angular velocity. In position 1, it's not moving, so my T1 is equal to 0. So really, my equation is V equals T2. So now I need to focus on solving T2. And T2 is this guy right here. So now we're going to focus on this part of the equation. So we need to look at which rigid bodies contribute to linear motion and which contribute to angular motion. Okay, so we have our first rigid body is BD. And we said that BD is undergoing pure rotation. So that means it's not going to have a linear property. It's only going to have a 1/2 I omega squared. So let's write that down. So it's going to be 1/2 IBD omega squared. And yeah, that's fine, omega squared. And then we have this next body. We said that ABC is undergoing planar rotation. So that means it will have linear component and an angular component. So let's write those down. So we have plus 1/2 IABC omega squared plus 1/2 mv squared. Now this v, where's the location of that v? That velocity is going to be located at the center of mass. On our diagram, that center of mass is located at point B, so I'm just going to put B, okay? Now, please don't forget you have 3 rigid bodies. You've only accounted for 2 right now. That slider does carry a mass, so you do need to include it. And you told me that the slider's in pure translation, so it will not have a linear, an angular property. So I have to include a 1/2 mvc squared. Okay, let's look at our knowns and our unknowns. I want to find omega, so that's good. I know that I could find i's, that's fine, I'm given m's. I don't know this one and I don't know this one. So let's first start by finding things that I can find pretty simple, right? So moment of inertia about BD. Bar BD is in pure rotation about its endpoint D. That means that its moment of inertia will be 1/3 ml squared. I know that because it's a slender bar and it's one of those moment of inertias that's very common that we know of. If I didn't know it and I only knew the moment of inertia about its center of mass, I could use the parallel axis theorem to take it from its center of mass to the axis of rotation. But again, this is fairly common. My mass of bar BD, I believe, was 3, right? I think. I'm pretty sure it was 3. Yeah, my mass is 3. So this is going to equal 1/3 times 3. The length of bar BD is 1 squared. This equals 1. Bar ABC is undergoing planar rotation and it's rotating about its center of mass. So now we can use the 1/12 ml squared. This is going to equal 1/12. The mass, I believe, was 6. The length is 2 squared. This is going to leave me with 2. I also need the mass of my collar, which was given, mass of the collar was given as 1 kilogram. The mass of bar ABC, 6, is going to be 6. Okay? Okay, we're getting there, guys. Hang in. All right, so now, so now I'm left with that. So let's go back up to our roadmap, because I'm sure at this point you're like, did I just go down a rabbit hole? Where am I? How do I get out? All right, I completed step 1, my free body diagram. I just completed kinetics because I used the 2 equations of motion available to me, but I'm still missing 2 unknowns. I need to find VB and VC in order to calculate omega. That's when step 3 comes in, your kinematics. How do I find the velocity of a point on a rigid body? There are 2 methods. Your first method is relative velocities. Your second is the instantaneous center. I'm going to use relative velocities for this. You're welcome to use whatever you like, okay? So let's go ahead and start that. So now we're at 3. We are at kinematics. And I need to find VB and VC. Well, VB, if I look at bar BD, you told me that point B is in pure rotation about D. That means that it's only has its angular component of relative velocity, which is omega cross B with respect to D. This is going to be equal to, my omega for BD is going in the clockwise direction, so I will have to have a negative omega K, cross RB with respect to D. So RB with respect to D, the length of our bar is going to be 1. And then we are looking at the theta, my goodness. So, but here's another part where you have to be really careful in. I want to find VB and VC at position 2. At position 2, please be very careful, because this, and when I'm looking at the vector, because this is BD, this is 1, this is theta. My theta at position 2 is equal to 30. So my RB is going to be 1 cosine 30I plus 1 sine 30J. Okay, so my VB is going to equal 0.866 omega. K cross I is positive J, but you have a negative out there, so that will be negative. Then I have sine of 30, which is going to be 0.5 omega. K cross J is negative I, but you have a negative here, which makes it positive. Now, VB in this equation is a scalar, not a vector. So you will need to calculate the magnitude here, okay? Some of you might be thinking, well, Dr. Walk, why didn't you just do VB equals R omega? I could have. That's not a big deal. You can do that. But when you go to find VC, you might need it in vector form, okay? So this would just equal 1 omega. So your magnitude, you could do that here. You could square both terms, but you're going to get equal to 1 omega. Okay, so this VB is no longer unknown. I can replace it with omega. Okay, so now let's look at VC. Well, VC is, I could relate B and C. So VC equals, bar ABC is in planar motion, so you're going to have a linear and angular component for velocity. You're going to have VB plus omega K cross RC with respect to B. So this is C. You're going, oops. That was weird. So this is point B. This is point C. I'm going to C with respect to B. So that means I'm going to have a positive X and a negative Y. So VC is going to equal negative 0.866 omega J plus 0.5 omega I plus omega K cross RC with respect to B. This is going to equal, we're going to have a 1 cosine 30I and a minus sine 30J. Okay, so VC is going to equal negative 866 omega J plus 0.5 omega I plus, now I have cosine 30 is going to be 0.866 omega, K cross I is J. And then I have my sine 30 is going to be 0.5. It is a negative, but K cross J is positive. And that's in the I direction. Okay, so my VC is going to equal, I have a negative and a positive, so this is going to cancel out. I have a 0.5 and a 0.5, oops, I forgot my omega, I'm sorry. I have a 0.5 and a 0.5 omega, so that's 1 omega I. And that makes sense because velocity is only acting in the I direction. However, when I plug this into my equation, I'm only going to put 1 omega because it's a scalar. Okay, I don't care about direction. And look at that, we have everything we need. So now we can write all of this out. So again, remember we had V equals T2. So our V, we said, was 53 plus 15.57 plus 3.91 minus 33.72 equals, okay, now on this one, if you plug in all of these numbers, you should get 1/2 omega squared plus 3 omega squared minus 1/2. And then I reduced that a little bit more. And I'm getting that omega is equal to 2.95 radians per second. And guys, you made it to the end of the video. I hope you made it to the end of the video and you're still with me. This is actually such a great problem because it, again, like I said in the beginning, it tests so many concepts, and make sure you really understand the difference between particles and rigid bodies, the difference between different types of movements or motions that a rigid body causes, and it makes sure that you understand, how do I deal with different types of forces? Is the force a function of position? Is the force a constant? Is the force a position of time? Anyway, I hope that that helps, and don't forget to give this video a like and comment below just your ideas and your thoughts going through the problem, and if you had any type of like hiccups or just your thoughts in general. Okay, I'll see you next time.